It's peaked more over here. Got it. Let's make sure I click the right button there so I don't get disconnected. So if you're looking at a red star, then it peaks over here in the red instead. So those are the differences between those stars that we were just looking at. If you're looking at something that's, say, more of the temperature that you'd get out your window, something that's room temperature, you're going to peak way over here in the infrared, which is why people don't glow when you look at them. But if you were to look at them with infrared eyes, then you would actually be able to see people in the entire environment around you glowing with this exact same kind of property. So that's not all that happens in stars, though, and it's got an underlying glow from the temperature of the object. But you also have physics from atomic transitions. So if you remember the hydrogen atom, then the electrons in the hydrogen atom are separated into discrete atomic orbitals or discrete energy levels. They can't have just arbitrary energies, but electrons in the hydrogen atom hop between these discrete energy levels. And when they do, they either emit or absorb radiation at very characteristic frequencies, very characteristic wavelengths. And so when you look at the spectrum of an object and you see a feature at 6,563 angstroms, that's one of the primary hydrogen lines, for instance. It looks red to us. So if you see something emitting in hydrogen gas, it'll often look kind of red in the sense that a lot of the power is coming out in this red line here. There's a host of other lines as well. And those get added on to that broadband continuum spectrum that we were looking at to tell you more about what's going on in an object. Depending on how it is you're seeing that object, it can look in different ways. If you have a source of continuous radiation, like a star here, if you look at it directly, you get a continuous spectrum. But if it shines through a cloud of gas or something in the way, then the atomic transitions in that gas can superimpose a grid of these so-called absorption lines on it. So it preferentially takes out the power in these lines that we were just talking about, these lines corresponding to the jumps between electronic atomic orbitals. And you'll see these dark features in the spectrum. Conversely, because that power, it isn't being lost, it's just being scattered out in all sorts of different directions. That if you look at the cloud of gas from the side, you don't see the continuum spectrum because you're not looking in the right way. You're not looking at the star anymore. But you're still seeing this cloud of gas. It's all lit up and glowing in these characteristic lines. So that actually turns out to be incredibly powerful as well, because it means that we don't need to have a light source right behind an object in order to see what's going on in it. Gas clouds can glow if they're lit up by something nearby. And in this case, stars have gas too. They've got an atmosphere around them. And that cloud of gas around the star gives these absorption lines, even in stars that we look at. So when we look at star fields like this, we can look and say, oh, it's a very pretty star field. It's got blue stars and it's got red stars. But we can measure the spectrum of those stars and actually say what kinds of stars they are based on what it looks like. The very bluest stars are these so-called O stars, these very hot, young-lived stars that they're very massive, they burn out very quickly. But while they're around, they've got this incredibly blue spectrum, peaked far in the blue or the ultraviolet, and they've got these strong hydrogen lines in them. Sort of more average stars, by the time you get down to kind of an A star range, they're not quite as blue, they're flatter, but you get very strong what's called Balmer break. And that turns out to be an incredibly useful feature in the spectrum because you can look for things like this very easily to tell what stars are A stars. Our star is more like a G star. It's pretty flat. It doesn't have much power in the blue. It doesn't have a lot in the red. It's kind of peaked around yellow or green. It's got some fairly weak absorption features, but they're still there. And when you go down to the very lowest mass cool stars, the so-called M stars, then you can see all of these other features in it corresponding not just to hydrogen absorption, but they're cool enough that you can get all sorts of molecular species producing features in these stars as well. So you can actually learn a lot about what's going on in a star or anything else you're looking at, though, not just by what lines are there. You can look and say, oh, there's a hydrogen line. The spectrum looks like this. It must be this kind of star. You can learn a lot from exactly where those lines are, too. So this is the classic Doppler shift, in the sense that if a source is moving towards you, it kind of scrunches up the wavelengths and shortens them, so that it's so-called blue shifted. Or if it's moving away from you, it lengthens out the space between the wavefronts and it's so-called red shifted. What that means is when you look at the spectrum of these objects, then something that unshifted might look like this. Now, here's your red hydrogen line. Here's a bunch of other lines you might have in your spectrum. If you see that spectrum and everything's shifted very slightly one way or the other, that's how we know what an object is doing in terms of how it's moving. Is that object moving towards us or away from us, and how fast? But the faster the motion you get, the larger the shift. So if you measured, say, this bottom one here in a lab, you've got a jar of gas in the lab, you measure what the characteristic wavelengths are of the transitions of that kind of gas. You look at a nearby star and it's a little bit shifted, maybe by 40 kilometers a second, 30 kilometers a second, something that astronomically at least isn't terribly fast. If you look at a nearby galaxy, it's going to be a little bit bigger. So here we're talking maybe a few hundred to 1,000 kilometers a second. If you're looking at a more distant galaxy, it's going to be shifted even further. And a very distant galaxy, it can actually be shifted incredibly far. So the line that you were expecting to see in the red might now be in the infrared, for instance. And this was actually quite a problem at first. And when people first started looking at spectra of very distant galaxies, these lines were shifted so far that people looked at the spectrum and thought, wow, that doesn't look like any spectrum I've ever seen before. There's lines in all sorts of weird places. Have we discovered new elements? And it turned out that wasn't the case at all. It was just that the lines they were used to seeing were shifted so far that they didn't even think to look that far away for the lines they were familiar with. And now that implies they're moving away from us incredibly quickly. So on galaxy scales, these kinds of shifts are how we see evidence for dark matter. So if you take a spectrum of a galaxy starting from the middle, you work your way out to the edge, you get a spectrum of each point and you ask, how far are the lines shifted away from the 0 point? Now you set your 0 point at the center because the entire galaxy will have some motion with respect to you. But with respect to the center of the galaxy, how far away from your individual parts moving? Because it's going to be rotating a little bit and you can pick up that rotation. What you see in many cases is as you go further out from the center of the galaxy, the rotation curve, as we call it, picks up, goes up, and then kind of flattens out, maybe 100 or 200 kilometers a second or something like that. And that doesn't match what we see in terms of the stuff in a galaxy. So if you can now look at the stars, you can add up how much stuff there is in a galaxy. Because there's, you can count the stars, if you will. You can add up the light and say, if the light that was in the galaxy is all the stuff that's there, what you'd expect is that rotation curve goes up and then turns over and tails off. And that's not what we see. There's this huge gap here between what we would expect and what we actually observe. And that gap is dark matter. By definition, it's the mass that we don't see. You can detect this mass by how it flings the stars around in the galaxy. But no, we have no idea what it is. That's something that's still very much a open question in astrophysics. If you go out even further on cosmological scales, then this is how we know the universe is expanding. So this is a classic figure from Edwin Hubble, actually, almost 100 years ago now, in which he looked at the redshift or the velocity shift of galaxies. He knew how distant they were because of a few tricks that he could play with variable stars to get the actual distance. And he realized when he plotted it that now the further away the galaxy was, the faster it seemed to be moving away from him. And the reason for this turns out to be that the entire universe is expanding, and that's what you're seeing when you look away on these very distant scales. And now many people have spent a lot of time refining this original diagram over the past 100 years, so we can do a much better job of it now. But that's the basic idea behind it. As you look further and further away, things are expanding faster, and our best explanation of that is expansion in the entire universe itself. So you can also do other things looking at spectra beyond just saying how fast things are moving, for instance. Because each element has its own unique chemical fingerprint in terms of the lines that it imprints on a spectrum. So hydrogen, for instance, I showed you earlier, that was the one that had the characteristic line in the red. It's got also a number of other lines in the blue. But each of these elements has its own unique set of lines that will imprint on a spectrum. Oxygen, for instance, has a very strong green line. So that's something that we're very familiar with if you study nebulas in astrophysics. If you see it glowing strongly in the green, odds are that's an oxygen line. You can often pick up strong lines from things like nitrogen, helium, and a number of these other low atomic number elements as well. So when you actually put this into practice in our solar system, here's an example of how that might work. If you were taking a spectrum of Titan, say, this is one of the moons of Saturn. So when you look at Titan, you see it glowing in the sky. What you're actually seeing is light that started from the sun, went all the way out to Titan, bounced off of Titan, and is now bounced back to us. And what we're measuring is a combination of all of those effects. Here's what the spectrum of Titan might look like. So you pick up this CH4 or methane band, and that's the actual atmosphere of Titan that we're seeing there. That's now absorption due to the clouds in Titan's atmosphere. It can tell us what atoms, what molecules are in the atmosphere of the moon that we're looking at. It's not always easy though, because you've got other stuff in that spectrum too. Here, for instance, is a hydrogen line. That's nothing to do with Titan, that's just the sun. And this is the sun's atmosphere in this case that we're seeing. It just doesn't shine light out efficiently at that wavelength. So it goes all the way out here, bounces off Titan, comes back to us, and it's still missing light at these wavelengths. So you need to be able to disentangle that. And finally, there's this feature, there's oxygen. It's not actually telling us that there's oxygen in the atmosphere of Titan in this case. That's oxygen in our atmosphere. So even if we look at the very most distant galaxies, the light from these galaxies can travel for, say, millions or even billions of years. And then in the final fraction of a second, right before it gets to our telescope, it passes through our atmosphere and gets absorbed in a number of things that we see in our atmosphere, like in particular oxygen and water vapor. And that turns out to be a real problem, actually, if you're looking at some wavelengths where the Earth's atmosphere is fairly opaque, which I'll come back to a bit later. So in practice, you need to disentangle where all of these absorption components come from, but you can learn about what's in a planetary or a moon's atmosphere in this way. You can do that around other stars as well. It's not just limited to our solar system. So one of the really neat things that we've been able to start doing in recent years is if you look at what's called transmission spectroscopy from transits. If you look at a star somewhere else in our galaxy, if that star has planets moving around it, well, sometimes the orientation is just right, so the planet can move in front of the star. And when it does, it produces a dip in the spectrum that you get from the star, because it blocks some of the light from the star. Not a lot, you've got to be able to measure tiny changes of order of % or so in the spectrum, but that's very doable now. And what you'll see sometimes is that you don't just get blocked by the planet, the rocky bit, but the atmosphere as well. So the atmosphere now also filters the light you get from the star. In some cases, what you can see is things like in the sodium line here, you get some kind of sodium absorption just from the atmosphere of the star. You get deeper sodium absorption when a planet's transiting, and that can tell you that you've got, say, sodium in the atmosphere of this planet that you're looking at. And that's one of the ways that we're looking to learn about what the composition of planets around other stars is with JWST and other telescopes. We can use this transmission spectroscopy to tell us about what's in those atmospheres based on the light that it blocks from the stars they're moving in front of. So if you back up for a minute and ask what we can learn from spectra, then it's really a wealth of information, and I'd argue it's how we know most of what we do about the universe. You can learn a lot from imaging and how bright things are, but it's really once you start getting into the spectra and looking at these lines that you can get into the physics of how the universe works. If you look at what lines are present, so you've got hydrogen lines, you've got magnesium lines, oxygen, etc., that can tell you a lot about the chemical composition of the thing that you're looking at. It can tell you about what the temperature and density of the gas is. If you look at how those lines are shifted, it can tell you about the kinematics, and it can tell you about the presence or absence of dark matter. So if this galaxy is blowing gas into its surrounding environment or accreting gas from that environment, and it can tell you about the expanding universe. You can look at how wide a line is. That actually tells you something about surface gravity and pressure, because it imparts a width to the line based on essentially how the physics is behaving in terms of how the kinematics are going on in the gas that you're looking at. If you're very high pressure, that line's going to be broadened. And you actually see this if you're looking at street lamps on Earth. There's narrow, well-defined mercury lines, but if you look at a mercury street lamp, those are very high pressure, so they look like very broad features you might see in your spectrum. That's another problem we have actually when we're looking at spectra of other things in the universe. The sky glows, so if you see Mercury and things that you're looking at in the sky, it might just mean you've got mercury lamps in your area that are making the sky glow. What I'm interested in most is galaxies. So I'm, of course, very interested in learning about extrasolar planets, active galactic nuclei, black holes, etc. But my thing is galaxies. So that's what I'm going to kind of focus in on for the rest of the hour or so, and show you just what you can get with galaxies and how you can learn about how they behave based on their spectrum. So here's now some characteristic spectra of galaxies, just to give you an idea of what we're working with. So you know that there's star-forming galaxies. Our Milky Way is a star-forming galaxy. It's not forming stars very fast, maybe 1 solar mass a year. You can have star-bursting galaxies forming stars much more rapidly, maybe 100 solar masses a year. And then there's so-called quiescent galaxies, things that are red and dead. They don't have any gas. They're not forming stars. They're elliptical galaxies. They're just evolving along the stars that exist already, but they're not forming new stars. And those look quite different. If you look at a starburst galaxy, for instance, you're picking up these strong hydrogen absorption features here in the blue. It's because it's got a number of young stars in it, if you remember the star spectra I was showing earlier. And it's got these extremely strong emission features corresponding to the ionized gas region surrounding all of those young stars. Star-forming galaxies like ours, they've still got these emission features, but they're not quite as strong. They've got a few differences in terms of the relative strength between them. And then by the time you get down to the quiescent galaxies, there's really not that much going on in terms of emission features. And you just see the absorption features due to individual features in the spectra of the stars themselves that you're looking at. So we've learned a lot over the last 100-odd years. We've been doing galaxy spectroscopy, but the traditional spectroscopy we've always done has significant limitations. So this is the state of the art of galaxy surveys as of about 20 years or so, 15 years ago, something like that. You have a galaxy like this. This is an image from the Sloan Digital Sky Survey. And if you want to learn about the galaxy, if you want to learn about large numbers of galaxies at a time, you need to do it in an efficient way. So you get an optical fiber and you place it on the sky at the location of this galaxy. In this case, it might look something like this. You get the spectrum from it. And from that, you learn everything we know about the galaxy in terms of how rapidly it's forming stars, what its history is, what its metallicity is, by which I mean the balance between how much oxygen, carbon, etc., how much iron does it have, how well is it enriched its interstellar medium. Everything we know about the kinematics, how a galaxy is moving, how it's rotating, whether or not it has a black hole in the center, etc. And that's great, but you can see it's really not terribly representative. We're just looking at this teeny tiny little bit in the middle here. There's a whole lot of other galaxy out here that we'd be interested in knowing about as well, and this middle isn't necessarily representative. For small numbers of samples, for small numbers of galaxies, people have worked around that by doing something called slit spectroscopy. So there you might place something called a long slit across the galaxy and get a spectrum through this entire region here. That's better in the sense that you can now compare what you get here in the outskirts of the galaxy with here in the middle and all the way here over on the other side. You can make some kind of a profile of the galaxy and how things change. But it's not really what you want. What you want is something like this, where you say, give me the spectrum everywhere. I want to see, what does the galaxy look like in the middle? Maybe there's an AGN there. What does it look like in the outskirts? Well, maybe there's gas falling into the galaxy there that I want to learn about. And while people have been able to study this for 1 or 2 galaxies, it's really been only very recently that the so-called integral field spectroscopy has taken off. And it can give us things like this, maps of the properties of galaxies. So you can make maps of star formation, say. In this case, I'm looking for strong hydrogen emission lines and using that to tell me about where star formation is happening. And you can see in this case that, might be a little bit going on in the middle, but there's this giant ring of star formation. You can see these spiral arm features in the star formation as well, which you would have had really no idea about if you just looked at the very middle or cut straight through the center. You can look at the stellar age. Here I'm looking for that characteristic break in the spectrum I was talking about earlier, the Balmer break. The strength of that break tells you something about the age of the galaxy spectrum that you're looking at. You can tell in this case that it's older in the middle and a lot younger in the outer skirts of the disk. This is the characteristic bulge disk difference. The bulge is a bunch of old stars. The disk is much younger, forming new stars all the time. And look at the rotation velocity. So you're no longer limited to, well, I think it looks something like this, estimating from the very middle here. You don't just have a cut through it in which if your slit went this way, you wouldn't see anything in the rotation velocity at all. It's just not rotating on that axis. With this integral field spectroscopy, you can pick up all of that information. You can look at exactly what the peak in the rotation velocity is. You can look at tiny kinks in the rotation curve and learn about how the stars are moving as an ensemble through that disk. So that's really what we've been interested in doing over the last few years or so. So this is a technique called integral field spectroscopy, where the idea is that you chop up a galaxy or a planet or a moon or whatever else it is you're interested in looking at into many pieces. You disperse the light from each of those pieces individually, and then you stitch it back together at the end. So you've got now an image of your galaxy, if you will, across in X and Y. You've also got it in depth and wavelengths. You've got the blue light, the green light, the red light, etc., and all the individual pieces of the wavelengths in between, so that you can look at the spectra and learn about what's happening at each point. That's what we've been doing in the latest generation of the Sloan Digital Sky Survey. So the Sloan Digital Sky Survey you're probably familiar with. It was started around 2000 or so, roughly 20 years ago. And originally it just took photographs of the sky. It took photographs of the entire sky that it could reach from the Northern Hemisphere anyway, in many different colors. And it used the color photographs of the stars and galaxies to learn a lot about them. But in later years, it's moved on to being primarily a spectroscopic survey. At first, just those tiny little pencil beams, individual fibers in the middle of galaxies. And in this latest incarnation, a IFU spectroscopy, we've now taken those tiny little circular fibers I was showing before and bundled them into hexagonal things like this. And so this is what we put on our galaxies, and this is how we get the spectra of individual parts of those. Here's what they look like in practice. You can't quite see the end of this in our actual lab photograph. So this is a slightly spiffified blow-up version of it, just so that you can see what the individual ends of it look like. But the idea is that each one of these circles in here is its own optical fiber that we can get a spectrum of. And then we can reconstruct the full galaxy from that. So you take these IFU ferrules, these individual optical fibers, and you plug them into plates like this on the Sloan 2.5 meter telescope in New Mexico. So the idea behind these plates, they're pretty big metal plates, they're a meter or so in diameter, and they're drilled with holes at very specific locations of the galaxies that you want to observe. And you take these optical fibers in these bundles and you physically plug them into those holes. It seems like a very low-tech technique, but it's been working remarkably efficiently for a number of years at this point. We're slowly phasing it out, so in the latest iteration of the survey going forward, we're actually using robots to do this fiber location placement instead. But for many years, we've actually just been relying on individual people who, during the day, they will get new plates, they will get the individual fibers, and they will plug them in those holes. We'll observe them that night. And then the exact same thing will happen with a new set of plates the next day. It's been remarkably efficient over the last probably 15 years that Sloan's been running this program, and the last 7 years we've been running it for MaNGA. It's allowed us to get a much larger sample of galaxies than anything that's really been possible to be achieved before. So as mentioned before, people have done IFU spectroscopy, getting spectra of the entire galaxy for probably the last 15 years or so, but those have usually been in samples of 3, 5, maybe 100 in some of the most ambitious such surveys. But it's really been very difficult to get large numbers until now this MaNGA program that we've been running. This is the mapping nearby galaxies at APO. And this is a survey that we've actually just completed as of the end of last year and working on the final data products for now, which we now have a sample of 10,000 galaxies that we've looked at with this IFU spectroscopy. So in this figure here, for instance, I'm showing you now, so the distribution of galaxy types that we're looking at. Each one of these dots is a single galaxy in our survey, showing you that now in terms of stellar mass, thing. We're looking at things with a star bulk, how much mass does it have in stars? Anywhere from 10 to the 9 or a billion solar masses, which as galaxies go is pretty small. That's right on the dwarf galaxy end, all the way up to 10 to the 11 or 12. So now we're looking more like a trillion solar masses. This is big, even for a galaxy. And now there's a wide range of galaxy types in there. We're looking at things that are rapidly forming stars, by which I mean in this case usually about 1 solar mass a year. Starburst galaxies are rare, and things that aren't forming stars at all, these so-called red and dead elliptical galaxies, and a real mix of things all the way in between. And we're looking at things that are relatively nearby. So we're talking about now understanding the modern universe, and with the entire optical range of the wavelength band. So all of the blue through red that you're used to, plus a little bit of the ultraviolet and a little bit of the infrared. So that really covers the majority of the classic diagnostics that people have been working with for many years to learn about what's going on in galaxies. So what I'm going to focus on now is what those emission lines can tell us about galaxy physics. So what's one specific thing that we've learned from this survey in terms of how the universe works? And I'm going to focus in on these emission lines that I've been talking about for a while. These hydrogen lines, the so-called H alpha line at the red wavelengths, the oxygen line at green wavelengths, etc. If you look at a nebula, for instance, like this, or a galaxy like this, these are the lines that you tend to see. These are the things that are obvious. I'm going to delve a little bit into physics for a moment, just before I sort of pull back to start talking about what this actually means. But you remember I mentioned earlier that when you're looking at the hydrogen atom, there's very characteristic energy levels in that atom that tell you about transitions between those levels that you observe for individual emission lines. You get the exact same thing for other kinds of atoms as well. So if you're looking at the oxygen line, for instance, you get similar things, transition between atomic orbitals here, between the S and D states, for instance. This is that famous green line I was talking about here. This is a green transition. And if you're looking at all sorts of different lines, the exact strength that you get in different lines, say the second transition of oxygen compared to the first transition of hydrogen, etc., that tells you a lot about what the density and the pressure and the atomic content of an individual nebula is. So you can make plots like this one, for instance, in terms of what is the metallicity of a nebula as a function of radius that you get from various different emission lines, etc. You can use the combination of the hydrogen lines and these metal lines to tell you a lot about what's going on in that nebula. They're ionized in different ways. For hydrogen, then it tends to get ionized, it kicks its electron off, and it's just a proton flying around. That proton then grabs onto another electron, it recombines, and the electron sort of chunks down through different energy levels, and each time it does, it emits radiation that we see. For the metal lines, those aren't necessarily ionized. They just keep on colliding with each other and keep on colliding with incoming photons. And that's what produces a lot of the radiation that we see. And different kinds of ionization structures produce different regions that are sensitive to things like temperature, the exact shape of the ionizing spectrum. Is it something that's very blue? Is it something that's very red? And you can learn a lot if you look at the ratios of how much power is coming out in different lines. So you can make plots like this one, for instance, where if you take the ratio between, in this case, the ratio between the nitrogen line and the hydrogen line on this axis, and oxygen and hydrogen on this axis, you can plot what you get for galaxies. So this thing on the left is from the original Sloan Spectra survey, where, if you remember, we're just looking at the very central regions of galaxies. And you can look at it and say, that kind of looks like two different regions to me. It looks like two different things going on. There's this characteristic curve here, and there's kind of some fluff up here. And about 20 years ago, Guinevere Kaufman and a number of other people before squinted at this plot and said, if I draw a line about like this, it seems to separate this blob down here from this blob up here. So let's call them different kinds of galaxies. And more or less, that's true. These galaxies down here are the star-forming galaxies. These ones up here are the active galactic nuclei, the black holes, the high energy physics, etc. And some very old and red galaxies over here as well. They kind of blend into one another. It's a little hard to tell them apart. We don't know exactly where that line is, but more or less you can tell this. And we build our physical models of how ionization works to match something like this. So this is just showing you a grid of star formation models saying, as different metallicities for galaxies, depending on what the total metal content is, you shift around exactly where you lie in parameter space. You might have slightly more oxygen, you might have slightly more nitrogen, but more or less you behave in this kind of a way here. But what we don't really know is exactly where that dividing line should be. And if you remember, we started from looking at this plot and saying, kind of looks like it goes there. That's pretty good, just based on where the density is of points. We'd like to see if we can do better than that. What we'd like to ask is if we can use kinematics to improve that. So now that we're no longer limited to the very central parts of galaxies, we can actually see the outskirts as well. We should be able to tell the separation between different regions of galaxies. So stars today form in a thin plane of cold, dense gas at the middle of a disk. So when you look at a disk galaxy, then you're actually seeing a number of different parts. So in this diagram here, I've kind of broken out the structure of a typical disk galaxy. You've got a bulge in the middle of the galaxy. That's usually kind of old, it's red, it's got a number of older stars, but not much in the way of gas. You've got a thick disk of stars that might have some thickness, maybe a kiloparsec or something like that. And then you've got a thin disk, and this is where the star formation is actually going on. So a very thin disk, very tightly confined to the disk midplane. That's actually where all of the new stars are forming. And so what we think we should be able to see is as you look at successively older populations, then those populations should get broader and broader and broader. And we should be able to see that in the kinematics. And I'll jump through pretty much all of the details of the data analysis and just say, yes, that is what we see. And with the MaNGA data, for the first time, we've been able to actually see exactly where this division is. We no longer need to wave our hands and say, well, there's kind of a cluster of points down here and a cluster up here. We can actually look at the kinematics and say, well, here are the ones that are dynamically cold, the things that seem to be in a thin disk. They've got these velocity dispersions, if you will. That's a measure of how wide the line is, that are down around 20 to 30 kilometers a second. That's this stuff. These are the star-forming galaxies. Up here is the stuff that's not star-forming. So if you look at black holes and AGN, those are now much broader. They've got a lot more kinematic excitement going on, if you will, in the sense that you're rocketing around the black hole a lot faster, and it's much more pressure going on in that gas. So we can actually redefine this dividing line here and say we can now use this to constrain our models and say this is the difference between star-forming and non-star forming parts of galaxies. You can break things up in a number of other ways as well. You can make a grid of plots, and I apologize for how dense this figure is. The main takeaway point to draw from it is that if you look at, say, age, or the radius in a galaxy, or the mass of a galaxy, these different regions really start popping out in terms of what their behavior is. So you can just take a lot of conclusions from this individual plot. You can look at, say, the so-called linotype galaxies. That lies in this region in the diagram. And you can just look at it and say, wow, those really stand out from these things. They're a lot redder than this stuff here. In this case, that means they're a lot older. You can look at things like radius, and you can measure the inside-out growth of galaxies just off of this one plot. You can look and see how the galaxies grow from the middle forms first, and then it becomes older and fades and becomes redder. As you look out at larger and larger radii, that's where the star formation is happening. Star formation gradually moves out in the galaxy with time. And you can find a number of other things from plots like this as well. So this has been one of the results I've been most excited about to come out of our survey recently, in the sense that we can really add the third dimension into plots like this, and not just look at the ratios between different lines, but look at what that's telling us in a physical sense in terms of how the gas is moving in these galaxies as well. That's been really fun. So that's just a small slice of the spectrum, though, and time's getting on in this talk, so I'd like to sort of move it to the next part of what comes next. And now I've been talking about optical lines. They're really in this tiny little window right here, lines in the red, lines in the blue, etc. Now, this is all of the spectrum that we can see is this tiny little band here. There's a much broader spectrum of things that we can measure about the universe, all the way from gamma rays down here up to radio waves up here. And depending on what you want to learn, you want to look in different parts of the spectrum. If you want to learn about really hot, high energy stuff, black holes, neutron stars, etc., you really want to look down here in gamma rays. If you're interested in sort of low energy, cool stuff, say you're looking at dust, you're looking at exoplanets around other stars, you're looking at young stars before they actually turn on and start burning hydrogen, then you want to look at these long wavelengths instead. And if you look beyond the visible, there's a lot more you can really do. That's hard from the ground because we've got an atmosphere, and I'm kind of partial to the atmosphere. I like having air to breathe and things like that, but it really does get in the way if you're trying to look at and learn things about the rest of the universe. So here's the visible window here. What I'm plotting here is just the percent that the atmosphere blocks incoming light. So this is the visible window. It doesn't block light very effectively in blue to red wavelengths. And well, there's a reason why we see it, the wavelengths that we do, is we're actually able to see through the atmosphere at these wavelengths. As you look towards the ultraviolet, though, it blocks it pretty quickly. There's a little range in here that's good for giving us sunburn, but we can't see very far into the ultraviolet. As you look into the infrared, you start seeing all of these bands coming in. This is oftentimes due to various water bands in the atmosphere that are blocking a lot of the incoming light. And in terms of life on Earth, that's a pretty good thing too, but for astronomy, it's pretty hard. You've got these few clear windows that you can look through, but especially by the time you get out to a few microns or so, it's really remarkably difficult to see very much. So if we want to learn much about the universe in something other than visible light, we can't do it from the ground very easily. There's a lot of information that we want to get at, though. So this is a couple of neat illustrations that I've seen, just showing how you can get information out of the infrared that you really just don't have at optical wavelengths. So if I showed you this picture, for instance, that there's two cups, which one has the hot drink in and which one has the cold drink? I have no idea. They look exactly the same. Similarly, if you look at this photo of somebody holding up his hand, if I asked you how many fingers is he holding up? I have no idea. You just can't see. It's completely blocked by this black bag that he's got on his hand. But this is an illustration in sort of a everyday life example of how you can get information from other wavelengths you can't from the optical. So if you take an infrared photo, suddenly it's incredibly obvious which one of these cups holds the hot drink. As I mentioned at the beginning of the talk, everything that has a temperature glows with a characteristic spectrum. And in this case, you can actually see this glow because you're going out to the wavelengths at which that glow is peaking. And you can tell, hey, it's the one on the left that has the hot drink. Similarly, here's a photo of the same person holding up his hand. If you're looking at infrared wavelengths, those wavelengths go straight through the black bag with really no problem at all. And you can see, in this case, all of his fingers are extended. You can still see the outline of the bag very slightly, but it's really not causing you any trouble seeing through whatsoever. And you can also see all sorts of interesting features like his glasses that are not only are they cooler than the rest of him, but they actually block light at these wavelengths. So in optical wavelengths, we can see straight through his glasses. Infrared wavelengths, you can't, which is kind of a neat property. It's the same kind of thing that we get in astronomy as well. Since if you're looking at a star-forming region like this, if you look in the optical, well, there's some structure here. It's hard to see. Most of it's just kind of dark in this region. But if you look in the infrared, you can start picking up all of the dust glow and a lot more of the individual features of the star-forming region that you just couldn't see in the optical. So what we're interested in doing now going forward, Hubble has really been limited to this band right here, ultraviolet, the visible, and a tiny little piece of the infrared. Spitzer has long been able to look at this light range here, so a good chunk of the infrared all the way out to almost microwave. But Spitzer's been very small. It hasn't had as much power as we'd like. So looking forward, what we're particularly excited about is the James Webb Space Telescope, which is the new NASA mission that's going to be the new Hubble, if you will, that it just about touches the visible wavelengths. But its real bread and butter science is going to be out here in the infrared, looking at things like we just saw in the previous part, the nebula, the dust, and all of that kind of radiation in the universe. So this is Hubble. It's actually pretty big on people scales in the sense that it's just over 2 meters in size, so it's going to be a bit taller than me. JWST is significantly larger, and it's going to be in space and have all of the benefits of that. It's got a much greater light gathering power than Hubble, and also, of course, different wavelengths as well. And there's a number of things that we're hoping to achieve with JWST. We're hoping to be able to look at so-called first light and reionization. Hubble's been able to allow us to look way back in the history of the universe to only a few 100 million years or so after the Big Bang. But JWST is going to allow us to push that even further to see the very first galaxies as they were forming, see the first light from stars that turned on in the early history of the universe. And it's really tracked that all the way up to the present day to see the history of galaxy assembly over time. It's going to allow us to look at the birth of stars and planets, going to allow us to do that transit spectroscopy that I was talking about earlier, where we look at little dips in the features of background stars that'll tell us about what the chemical and molecular properties of the atmospheres and planets around other stars are. They tell us about what's on those exoplanets, and excitingly, if, for instance, we see any hallmarks of if we see oxygen in those planet atmospheres or other things that might be indicators of potential life, that'll be a very exciting result. It's got a lot of different observing modes on JWST. So this is just a snapshot of what the field of view of the telescope looks like. So it's got sort of classic imaging modes. This is the near-cam cameras here. It's got a variety of different spectroscopic modes, both from the near-infrared, NIRIS, near-spec, and MIRI. And there's a ton of different ways we can use this telescope. So we've got classic imaging. We've got dispersed slit spectroscopy. We've got what's called coronography, which is where you block out the light from a bright background source so that you can just look at the faint things around it. That'll be good for looking at planets around other stars. And there's a variety of different things we'll be able to do with it. There's these so-called 5 instruments on it. There's the fine guidance sensor. That's essentially how we determine where to point the telescope. We look at where the stars fall within this field of view, and we determine how to slew and point the telescope so that we actually get what we want in the other cameras. There's the near-cam instrument. This is the main imaging workhorse of the telescope. It's going to do photographs, if you will, in lots of different color bands, all the way out from the optical to about 5 microns or so in the infrared, and a tiny bit of spectroscopy as well. Near spec is going to be the spectroscopic workhorse in the near infrared for many things. It's got a ability to do multi-object spectroscopy, so you can get spectra at lots of different locations through the field. NIRIS is a kind of neat instrument that allows you to do something called aperture masking interferometry, which I'm not going to go into detail on, but the upshot is it allows you to get much higher resolution than you might ordinarily be able to get using some complex mathematical transforms. It's pretty neat, but also kind of complicated to use. Then MIRI is the instrument that I work on. So this is the mid-infrared instrument going out from about 5 microns to almost 30 microns or so, so way away from the optical. Now we're really into the regime in which dust glows. And this is going to do both imaging and spectroscopy and this coronography as well, so that we can look at the properties of planets this far out into the infrared. What I'm most excited about, though, is that JWST is also going to put the first near and mid-IR integral field units into space. And so all the stuff I was talking about earlier with the things we've been able to learn about nearby galaxies from MaNGA and the Sloan survey, with these integral field units that map all the way across the galaxy, we're now going to be able to do this in space for things that are much further away with these integral field units. So we're going to be able to learn about what the properties of galaxies are now back much further than we've been able to before. So here's a spectrum of a galaxy, for instance. This is showing more of the spectrum than I've been able to show before. I focused on just the optical range before, so I was really just showing you this little bit right here before. Now I put it on a logarithmic plot, so I can show much more wavelengths. And now I'm going from the rest frame ultraviolet, showing the Lyman alpha features, another important hydrogen line here that usually we can't see because it's in the ultraviolet. and I'm going all the way out to a few microns or so. So now this is showing now these so-called PAH, or polycyclic aromatic hydrocarbons. I always stumble over that phrase. That's why people often call them just PAHs for short. This tells you a lot about what the dust properties are in a galaxy. And now we'll be able to see those for the first time in great detail. We'll be able to see it at a range of different distances as well. As you remember, I mentioned earlier, as you were looking at galaxies that are now moving away from you faster and faster, the light redshifts. What that means is that at redshift 0, or today, then with JWST, you won't quite get this hydrogen alpha line, but no, that's okay. We've got that in a lot of other ways from telescopes from the ground. We'll pick out a lot of infrared type features, and especially all of these new features out here, these dust features in galaxies. That's going to be the bread and butter of JWST in the nearby universe. As you go out to higher and higher redshifts, so earlier and earlier in cosmic time, when things are racing away from you faster and faster, that essentially shifts the wavelengths that you can look at, so that now you'll be able to push down to lower and lower regions. So by the time you go out to a redshift of 8, say, this is a very early universe, we're actually going to be using an infrared telescope to look in the ultraviolet, which is a little weird, but it turns out to be very powerful, because this Lyman alpha line, it might be in the ultraviolet now, but we're redshifting that line so much from early times that it actually turns into infrared light that we're looking at. And that'll allow us to pick up this classical suite of oxygen hydrogen lines that I was talking about for most of the last 45 minutes at much higher redshifts. We'll be able to see those lines from galaxies in the early universe, so that we can do the same kinds of analysis on the very first galaxies that we've been able to do on the nearby galaxies in the last few years. We're almost there. We've been working on JWST for a very long time now, but we're almost at the finish line. The final ground deployment tests are underway in Southern California at the moment. Here's a wonderful photo of the observatory from just a few weeks ago, showing one of the final tests to make sure that we can deploy the sun shield okay. I've seen the telescope in a lot of different phases as it's been assembled. The very first time I saw it, I think it was just a shell that didn't have any of the mirrors in the individual primary mirror segments. And being able to see it now actually all put together with the sun shield out and deployed is now really incredible, seeing it coming together like this. The sun shield is an important component of JWST in the sense that we're looking out in the mid-infrared. I mentioned that we're looking at things like cold dust. What that means is that if you don't block the telescope from the sun, it's not going to be able to see anything. It's got a gigantic flashlight shining on it all the time. So the sun shield is incredibly important in blocking the radiation from the sun so that it doesn't get superheated and A, destroy the telescope, and B, block out the light from the stars that we're actually trying to look at. But it's almost there. It's in final tests and should hopefully be shipping to the launch site fairly soon. Scheduled to launch on a rocket later this year, and all of us who've been working on it are going to be sitting biting our fingernails this whole time, because of course it's a very expensive telescope, worked on for a very long time, and you have to strap it to a gigantic rocket and launch it into space, and that's a very nerve-wracking time. But after a few minutes or so, hopefully the nerve-wracking part will be done, and we can actually get to work on now the 6 months that we need to actually turn it on. So it's going to launch from Earth, and over the course of about 2 weeks or so, is going to gradually fly out here to orbit around a place called L2. L2 is a special place in the solar system that just based on how the gravitational pull from things like the Earth, the sun, the moon, etc. work, then there are a few places in our solar system that are sort of stable points, and it can kind of orbit around that point as if there was something there, even though there's nothing at L2 other than a bunch of satellites at this point in time. But you can still orbit around that point somewhat efficiently as if there was some mass there, just because of how orbital mechanics works out. And it's going to take a couple of weeks to get there, and then we start 6 months or so of commissioning, in which we gradually start turning on all of the instrument systems. We need to cool down the telescope. Part of it will just cool down because it's going to be in space and it's got a sun shield, that's going to be cold. But for MIRI, we actually need to turn on a active cooler to get down even colder still. We want our part of the telescope to be less than 10 Kelvin. And that's going to require some active work to get there. Once we get cooled down that far, we can turn on our instrument and see what we see and do a lot of calibrations, and hopefully by the end of 6 months, be ready for doing some of the science we're interested in doing with the telescope. It's going to be an exciting time. I'm looking forward to it. And hopefully by this point in time next year, we'll be done with that and we'll be starting to do science. So I've been talking for nearly an hour now. I should probably stop there and say thank you. And I'm happy to answer any questions you might have.
Thank you so much, David, for this beautiful presentation. If any of you would like to ask a question, please feel free to unmute yourself and ask your question, or just type it in the chat box.
Let's see if I can open the chat window.
Don't be shy. Okay, we have a couple of questions from Instagram, so I'm going to ask them. Well, first of all, why is the mirrors of JWST gold-plated?
So the real reason actually is because gold turns out to be a very efficient metal for reflecting infrared light. So what we want to make sure is that we collect all of the light that's incident on the mirrors and actually get it into the instrument so that we can look at them. And the most efficient way of doing that is actually having them be gold plated, just because the reflectance profile is correct. And it's a side benefit that it looks very characteristic. It gives JWST a very iconic look, but the real reason is just because that reflects the light the best.
Okay, excellent. There are a couple of people who want to ask a question. Just a second so I can fix the settings, please.
In the meantime, I can see a question in the chat about what will JWST tell us about our galaxy. So there's a few things it can tell us about our galaxy itself. In terms of the stuff that's in our galaxy, it'll be able to tell us a lot about the other planets in our galaxy, because our galaxy is really the local universe in which we'll be able to learn most of what we know about planets. And I'm unmuting myself so I can keep talking. That's the region where we'll be able to learn the most about planets around other stars, and because you can't see them outside our own galaxy. If we want to learn about the properties of stars, it's remarkably difficult to see stars outside of our galaxy as well. So it'll be able to tell us a lot about the chemical composition of stars in now the Milky Way galaxy. And that's useful for being able to tell us about the formation history. If you can measure the chemical properties of stars in our Milky Way, you can start tracking them back to where they came from, how they might have formed, and etc. It'll tell us a lot about the dust in our galaxy that we haven't been able to tell in the past. Dust is a major component of what we get in lots of other galaxies as well, but it's remarkably hard to see. Mostly you just detect it by virtue of it blocking the light from the stuff that you're interested in seeing behind it. So being able to actually look at the emission from dust itself in the Milky Way and other galaxies will tell us a lot about how it's distributed, how that dust behaves, how it was formed, etc., which you can use to learn about the history of the galaxy itself. Let's see, I can just go down the chat window if you want, or if you want to add other questions as well. I don't know how you want to do that.
Yeah, let's answer the chat box first. Okay.
So next one, in general, if you want to be an astronaut, I'm not the best person to talk to that because I'm pretty far from being an astronaut myself. I don't think I'd do terribly well with it, but the best recommendation that I can make is if you have a degree in physics or something like that. And then oftentimes in the US, at least, being a part of the military test program is one way people often get into it. So you start off in various branches of the military. There's a lot of people who've got into astronaut training in recent years who've mostly just come from the sciences. And there I'd recommend a degree in a hard science is really part of the best way to come in. There's a call every few years, I know, for new astronaut classes that are incredibly competitive. I know a few people who've submitted applications to those. They didn't get selected, but it was 1 in 10,000 or something like that for the people who did. It's a very difficult thing to go towards, but now starting with a degree in the hard sciences and is a good place to start.
Okay, thank you. We have got another question from Muhammad. In the beginning of the meeting, Professor David mentioned dark matter, which we are all familiar of. But yet physicists are still debating over the nature of such mysterious matter, which remains undetected. What is Professor David's own interpretation or thought on